Good morning. Today in Math 125 we're going to talk about section 7.4, estimating a population mean. And you may ask, well, wasn't that the same title as section 7.3? Well, kind of. It was the same up to this point, but then there was a subheading, as you might recall. In section 7.4 we are going to assume that the population SD, the population standard deviation, and remember the abbreviation for that is sigma, we're going to assume that that is unknown. Right? Recall in 7.3 we were estimating population mean. Well, remember the population mean is mu, and we made the assumption that sigma, the population SD, was known for section 7.3. So 7.3 and 7.4 we're estimating mu in both sections. The only difference here, sigma is unknown in 7.4 and sigma is known. Okay? Alright, I want to back up and get a bird's eye view of what we've done in the chapter so far, because a lot of what we were doing builds on what we've done before. Isn't that always true in a math class? Let's talk about the first section we talked about in chapter 7. It was estimating population proportions with some desired characteristic of interest. And the idea we're here in 7.2, we've got some huge population to deal with, perhaps millions of candidates in this population. Our population proportion with some desired characteristic of interest we labeled as little p, and typically because populations are so huge we never know for sure what little p is. Alright, so what we did in 7.2 to estimate little p, we created a confidence interval based on sample data. Alright, so what we did was take a sample, and from that sample we garnered a sample proportion which we titled z hat, and based on that sample data we could make an inference about the population data. More particularly, based on the sample proportion we can make an approximation of the population proportion. Alright, we created a boundary of values on the real number line, centered at p hat, centered at the sample proportion, and we marched up and down a ways on the number line from p hat by the distance of what we call a margin of error. You recall we did this by hand in class, also using the one prop z int operator on our calculators, where our margin of error in 7.2 was obtained via this formula. Of course, we know that the TI 8384 calculators would compute this value upstream and come out with a interval without much sweat. So remember, in 7.2 we use the one prop z int command on the TI 83. Alright, so that reviews section 7.2, estimating population proportion. What about 7.3? Recall section 7.3. We estimated a population mean. Well, population mean is mu. Very similar idea. We've got a huge population, perhaps with millions of measurements. Right? There is a population mean for some value of interest. we label it with the Greek letter mu, but again, typically we never know exactly what mu is because populations are too big to count. So we're going to estimate, or we estimated mu much in the same way we did in section 7.2, but instead of estimating a population proportion, here we're estimating a population mean. So from here we garnished the sample, computed a sample mean, and we will create a bucket, an interval based on sample mean data that hopefully will contain mu. Alright, our margin of error for this section 7.3 was very similar formula, z sub alpha over 2 times sigma over the square root of n. Alright, and of course the TI-83 computed this upstream for us, so we used the z interval command with regard to problems in 7.3, estimating population mean with sigma known. Remember, we assumed that sigma was known in 7.3. Alright, the z interval command. Alright, one thing I want to jump on now before we get too far in section 7.4, there was an unrealistic aspect of 7.3. And I'm going to fill you in on this now because 7.4 is designed to deal with it. Alright, we estimated mu, population mean, with sigma known. Alright, but if sigma is known, that means you know what mu is. Right? So let me write that down. Sigma is known, but we need mu to compute sigma. Remember the formula for standard deviation? All right. To compute a standard deviation, you need to know the mean. If you recall, the formula for a population mean, well, basically you add up all the scores and divide by the number of scores. If we go back to chapter 3, sigma, you might hopefully recall this formula to compute standard deviation. The difference from the mean squared, add up all those squared differences, divide by n minus 1, and take the square root. You'll recall this formula from chapter 3. But notice, mu is involved significantly in the formula for sigma. So, again, if we know sigma, that means you must know mu. Well, so if you know sigma, why are we estimating mu? And that's a good question to ask. Right? So that's one perhaps unrealistic aspect of 7.3 is that you know sigma. The moral of the story here is it may be unrealistic to claim sigma is known. The book gets around this by comments in the homework problems like a past study has shown sigma to be whatever ... Or they may make a comment in some of the homework problems, historically sigma is assumed to be in whatever context the problem is talking about. Alright, well, the idea here is we are going to extend the concepts of section 7.3, but we're going to deal with that perhaps unrealistic aspect that sigma is known. So here we go with section 7.4. How to estimate mu, population mean, if sigma is unknown. So remember, the title of it is Estimating Population Means with population SD unknown. And that's what the formal title of 7.4 in the book. Alright, what we're going to do. It's going to work in much the same way. We've got a huge population. Alright, from this huge population, we are wondering what the population mean of some measurement of interest is. Alright, you'll never know mu for sure, so what I'm going to do is grab a sample. And remember, your sample mean is x bar. So what we will do, again, to estimate mu, create a confidence interval based on a margin of error parameter. Right? But in section 7.4, the formula for margin of error is going to change. Let me give it to you here. Our margin of error is E. Remember, in 7.2 there was one formula for E. In 7.3 there was another formula for E. In 7.4 there's going to be yet another formula for E. And it's going to look much like the formula for E in 7.3. But instead of a Z distribution, we're going to use what we call a T distribution. We'll talk about that in a minute. And instead of a population SD sigma, you're going to use a sample SD S. So let me write this down and recall in section 7.3, your margin of error was Z sub alpha over 2 times sigma over root n. Remember, in 7.3 we assumed that sigma was known, and that enabled us to use what we call a Z distribution to compute E. Alright, notice in 7.4 formula, we are using S instead of sigma in the formula, and instead of a Z score, we're going to use what we call a T score or T distribution score. So the mechanics of it are largely the same. Of course, the calculator is going to make it easy for us to grind out these intervals, but I do want to show you a little bit of the background before we calculate some estimates. Let me get a fresh screen here. Let's talk about that T distribution. Well, don't panic. The T distribution looks a lot like the T distribution, Z distribution. Let me say that again. The T distribution looks a lot like the Z distribution. Very similar. If I was to graph one on top of the other, you might not be able to see very much difference. Let me write this down. I'm going to say it's similar to the Z distribution. But it allows for greater variability seen in small samples. Alright, the t-distribution is bell-shaped, just like the z is. The t-distribution is symmetric about the mean, just like the z is. The mean of the t-distribution is 0, just like the z-distribution. Well, what's different, and I suppose to make it very clear and perhaps a little bit informal, the t-distribution has fatter tails than the z-distribution. Alright, if I was to draw a particular t-distribution on top of the z-distribution, well, let's say I start out with a z-distribution. Let me draw this in purple here. Let's say that's my standard z curve. If I was to graph a t-curve on top of it, well, basically you get fatter tails. Data's more spread out than in the z-distribution. Right? And again, this t-distribution, I have mentioned upscreen, allows for greater variability seen in small samples. In other words, you got more of a standard deviation or fatter tails in this bell-shaped distribution. Alright. Note, the TI-83 and 84 will calculate E upstream for us, really in all three sections, 7.2 and 7.3 and 7.4. But remember, if sigma is unknown, which is a more realistic scenario than saying sigma is known, and if you want to estimate mu with a confidence interval, you've got to remember that your margin of error is based on the t-distribution, because as we'll see, we're going to be calling up a command that involves that t-name. Hence, we will use on the TI-83 the t-interval command. Now, remember in 7.3 we use the z-interval command, but in 7.4, if sigma is unknown, you've got to remember to use the t-interval command. Let me show you what it looks like, this t-interval command on our calculator. Again, you press Stat button, look at the Test sub-menu, scroll down to t-interval. And we should see a familiar screen. It asks you what mode you want to operate in, data or summary statistics. And we're going to start with summary statistics, at least in the first couple of examples. Then they prompt you for a sample mean. Okay, much like 7.3. Notice, cap SX in TI language, remember that's a sample SD. Well, if you're going to plug in a sample SD, that implies that sigma is unknown. Remember, sigma is your population. Sigma is your population SD. So sigma is unknown. Hence, we're entering in a sample SD instead of a population SD. Okay? And notice the calculator, once you hit t-interval, the calculator recognizes that your population SD is unknown and prompts you for a sample SD. Alright, we're then asked for a sample size, and of course the familiar confidence level, and then calculate. Alright, so the framework is largely similar to 7.3 as we can plainly see. Alright, I want to look at an example, work out I think 3 examples from the book. Actually 1 example and 2 homework problems. I want to look at example 2 on page 358 in our text. Let's see if I can read it here. I'm sorry, 3. Let me pause. Alright, yes, example 2 on page 358. Constructing a confidence interval garlic for reducing cholesterol. Let's read through this problem. A common claim is that garlic lowers cholesterol levels. In a test of effectiveness of garlic, 49 subjects, let me write that down. 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after. The changes in their cholesterol levels have a mean of 0.4. Sample mean of 0.4. And a standard deviation, and by implication, that's a sample standard deviation of 21. Alright? Based on etc. Use the sample statistics that I've just written down to construct a 95% confidence interval estimate of the mean change in cholesterol level. Okay, so I think we get the picture here. 49 subjects undergo treatment, and you've got a sample mean and a sample standard deviation from this sample treatment, and we want to put in a compute a 95% confidence level estimate, or a 95% confidence interval estimate, for the population mean of net cholesterol changes for all subjects that undergo this treatment. Okay? Alright. Press your Start button. Go to the test submenu. Notice sigma is unknown. So we're going to use the t interval operator. Remember, if sigma is unknown, we're using a t-score upstream to generate E, so we must use this command, the t interval command. Alright, let's walk through it this first time out. For input, well, we are given summary statistics, so I'm going to want to highlight and select the statistics input mode. My x bar, my sample mean is 0.4. My sample standard deviation is 21.0. The sample size is 49. The confidence level is 0.95. Alright, so if you punch all this out on your calculator will return the following confidence interval estimate for mu. Alright, so again, we like to present these in double-sided inequality fashion, much like we've done in 7.2 and 7.3 before. I'll label it, this is my 95% confidence interval for mu, where mu is the population mean cholesterol level change under all subjects undergoing this treatment for all time. Okay? Alright. At this point, you might be asking yourself a question. Do I use the Z or do I use the T interval command? Let me put this heading. When to use the Z interval command or the T interval command. Alright. Well, in wide strokes, again, there's some details that we're kind of glossing over. But in wide strokes, the z-interval command is used to estimate mu if sigma is known and if the overarching population from which the sample is drawn is normal. Then we use the z. Okay? If sigma is unknown, then recall we are using the t distribution to compensate for the greater variability seen in small sample sizes, and if the population is also normal from which the sample is drawn, then we use the t interval command. Alright, so it's largely whether sigma is known or not known that depends which of these commands you're going to use on your calculator. You get a fresh screen. I think there's two more examples I want to do today. This is, I believe this is from your homework list, number 19 on page 367. So let's read through that example, number 19 on page 367. Mean body temperature. Dataset 2 in Appendix B includes 106 body temperatures for which the sample mean temperature is 98.2 and the sample standard deviation is 0.62. Alright, let me write that information down before we go on. Alright, we've got 106 body temperatures in our sample. The sample mean temperature was 98.2 in degrees Fahrenheit, and the sample standard deviation is 0.62. Now notice there's no neon sign lighting up that tells you sigma is unknown. Well, you have to sometimes squeeze that out from the given information and the context of the problem. So, and that's key. That really tells you which distribution we're using here, right? Alright, so sigma is unknown, and I judge that because they give us S, but they don't give us sigma. And when sigma is unknown, we're going to use the t interval to base our confidence interval on. Okay? Alright, point A. Well, they ask us for a point estimate of our population mean for healthy adult body temperatures. Well, the best point estimate of mu is going to be your sample mean. Alright, so that's all they're getting at here. If you're looking for one number to estimate mu, it's going to have to be your sample mean. I suppose that's the best we could hope for. Again, a better way is to create a confidence interval estimate for mu, and that's what we're going to talk about in part B. Using the sample statistics, construct a 99% confidence interval estimate of the mean body temperature of all healthy humans. Alright, so they want a 99% confidence interval. We've already written down our given information. Let me walk you through it with the calculator again. For input, first we hit stat, then tests, and then t interval for reasons we've already talked about. You want stats for the input mode because we are given summary statistics from the sample. The sample mean is 98.2. The sample standard deviation is 0.62. The sample size is 106. And the confidence level for this confidence interval is going to be 0.99. Alright, highlight calculate and then hit enter, and I get the following result. Here is my 99% confidence interval estimate for mu, the population mean of all healthy adults of all time, their temperature, right? All right, so let me write that down, label it. This is my 99% confidence interval for the population mean of all healthy adult body temperatures. All right, one more I want to talk about, and I'm going to use the same command but in the data input mode. 27A, let's check out 27A in our textbook. 27A is on page 368. All right, and they list, well, let me read the problem. It says listed TV salaries, number 27, TV salaries. Listed below are the top 10 salaries in millions of dollars of television personalities in a recent year, listed in order from Letterman, Leno, Korek, etc. I'm going to do part A. Use the sample data to construct a 95% confidence interval for the population mean. Well, notice in 27A they don't give us summary statistics. They give us raw data. And in that case, it's entirely possible that we could use the data input mode of our t-interval command. Alright, so what I'm going to ask you to do is go to L1, hit stat on your calculator, and then edit. And I imagine you're familiar with this process. Clear out L1 and then enter in the new data and number 27 into L1. Alright, if I look at these numbers as they're printed in the book here, they're supposed to represent the salaries of talk show hosts, so in millions, so 38, 36, 35, 27, 15. List all those numbers in list L1, and then we're ready to grind out our confidence interval. Alright, once you've entered in the new data, here we go. Press stat, test, t-interval. For your input mode, of course, we are going to use raw data, so make sure that's highlighted and selected. Notice the screen changes, the input screen changes, as you might have expected. We are no longer prompted for a sample mean and a sample standard deviation. Right? They ask us for a list, and if you put the data into list L1, L1 should be the default there. Frequency equals 1, that just means how many times are we going to repeat this list in our calculation, and the confidence level is then 0.95. Oh, and again, I use the t-interval because sigma is unknown. And again, there's no neon light that comes on. You just have to notice that sigma is not given, hence we have to assume it's unknown, hence we are going to use the t-distribution or the t-interval command to compute our confidence interval. Alright, I punched this out. Alright, so this is my, well, let me label it. This is my 95% confidence interval estimate for mu, where mu is the population mean salary for all talk show hosts of all time. Let me write that down. Mu is, it's kind of an abstract idea. It's the population mean salary for all talk show hosts of all time. And remember, we are basing this estimate, this confidence interval estimate, on sample data from our 10 talk show hosts listed. Alright, we were hitting the 35-minute point, so we'll call it a day. This concludes section 7.4, estimating a population mean with sigma unknown.